Okay, welcome to the electric current and Ohm's law slash electrical circuits notes. I want to quickly review the notes that we've already done in class. Hopefully, this will help you in your preparations for the test. Let's talk about what electric current is. The continuous flow of electric charge. It is the constant movement of electrons. Just like water is a current, will move down a river. Electricity is a flow of electrons that will go through a wire or any kind of conductor. The current's unit of measure is the ampere, but it's generally shortened to the amp. And then we'll see in a bit that it's in Ohm's law, the variable tends to be I, which, is not the easiest to remember because I is not related to electric or current. Two types of current. You have AC and DC. And AC is what we have in our houses, electric current that regularly reverses direction. It goes one way and then it comes back another. That's hence the name alternating current. It goes to and fro. Direct current, on the other hand, is flow in one direction. Battery-operated devices work this way. It's why your cell phone will charge quicker on a car charger than it will an alternating current or your home plug-in, because on alternating current, electricity flows to the object and then it comes away from the object, and it kind of ebbs and flows back and forth to it. Whereas direct current in your car will continuously charge that battery. Does it much faster because of that. Basically half the time. Sometimes even quicker than that. Let's talk about conductors and insulators. Conductor is any material through which electricity will travel easily. Metals are basically your good examples. Copper and silver are good electrical conductors. Gold is a very good electrical conductor. And electrical insulators are materials through which charge cannot flow easily. Some charge will flow through these things, but it just doesn't flow as well as metal. And it has really to do with the atom spacing, to be honest with you. Metal is very, very dense because the atoms are touching right next to each other, whereas in plastic or rubber, they're not exactly close to each other, relatively speaking. So anyway, wood, plastic, rubber, air, glass, all these things are insulators. Let's talk about resistance. It's the second part of Ohm's law, which we're getting to. We haven't got there yet, but we talked about current already, which is the flow of electrons. Resistance is the opposition to the flow of charges in a material. The unit for this is called the ohm, O-H-M. It's named after George Simon Ohm. We'll look at his picture in just a minute. And basically, resistance is things that slow down the electrons. Kind of like speed bumps slow down a car going down a road. So what slows down things? Material's thickness. If it's super thin, not as many electrons can pile on it. If it's super long, it takes more voltage on the front end to send more electrons that long distance. And temperature affects its resistance as well. Things that are cold will conduct much, much better because this goes back to the heat ideas, thermal energy. When things are cold, they tend to condense and come together. Well, the atoms are closer together, it will conduct better. So if it gets hotter, it doesn't resist as well. I'm sorry, it resists a lot. So cold things do not resist, hot things do. Well, this is a problem. This is a daily problem in electronics when computers are getting hot and resistance starts building up. Anyway, let's move on. I'm sorry, I should have explained these. These little box things here are resistors, built-in resistors to slow down the flow sometimes if there's too much current going to something. But also light bulbs, anything that converts electricity to something else is actually a resistor. It's resisting the flow of electrons. Voltage, the potential difference. Difference in electrical potential energy between two places in an electric field. The SI unit is the volt. What does that mean? The electrical potential energy. It's similar to potential kinetic conversions. One end having essentially 0 and the other end having, another number, for instance, like a 9-volt battery. In order for charge to flow in a conducting wire, the wire must be connected in a complete loop that includes a source of electrical energy. Now, the electrical energy is generally produced by something like a battery or power source, and it produces this with the volts. This is where the volt comes in. It provides the potential difference. So you have to have them connected in order to have potential difference. This is what we're getting into in the next second here is circuits. If you don't have it connected, it doesn't have potential difference. So now, this is what we've been working on. Ohm's law. You can see the guy down here in the bottom right, George Simon Ohm. He's the guy that came up with this principle. The voltage V in a circuit equals the product of the current I and the resistance R. It's a simple formula. V is equal to I times R. V is measured in voltage, or its voltage is measured in volts. I is current, measured in amperes or amps. Remember I said that earlier. R is resistance, and it's measured in ohms. Increasing the voltage increases the current. That's really what you need to walk away from with Ohm's law. If you increase the voltage, the current increases. If you decrease the voltage, then the current decreases. Something else. Keeping the same voltage and increasing the resistance decreases the current. That's what the formula shows you. They're inverse. When one goes up, the other goes down kind of thing. So keeping the same voltage, increasing resistance decreases the current. What is this saying? When you have more resistance, it slows down electrons more, right? Well, that's going to make the flow of electrons not go as fast. And it's totally intuitive, which means it makes sense if you think about it. Let's move on to circuits. We're going to be looking at simple circuits. These are complex circuits. So what is a circuit? A complete path through which charge can flow. If you remember back to the potential difference and the voltage one, this is what's required for potential difference or the volts to flow. So when a circuit's broken or open, the current has nowhere to go and stops flowing. Two types of circuits. One type is the series. This is primitive kind of circuits where you have only one path through which it can flow. If one element, like for instance the light bulb, stops working, none of the elements can operate because the circuit's been opened. The circuit has to be closed in order for the volts to transmit from the battery or from the power source. It needs a plus and a minus. Got to have that potential difference between them. Now, if you look at the example up here, if I take this light bulb out, there's a gap in the circuit, a gap or a break, and that's what it means. It means it can't flow, right? Electricity won't jump this little gap here. Can do it, but it typically won't do it, and it won't do it at a consistent rate. If you add bulbs to a series circuit, increases resistance, lowers the current, and therefore the bulbs are less bright. Because every time you add a bulb, it has a little piece of metal in it which increases the resistance. And every time the resistance is increased, less electrons are able to flow. As a result, the bulbs are less bright. Inversely, you take a couple of these light bulbs off, just have one, it's going to be brighter, right? It has less resistance, same volts, more current. Ohm's law at work. Last type is the parallel circuit. This is the type that you have in your house and in school and buildings, in your car too. Circuit with two or more paths through which charge can flow. It's kind of weird to think about parallel in the sense that, in mathematical sense, parallel is two lines never touch, this kind of thing for infinity. That's not really what it means here. And although this diagram has, three lines that are parallel, that's not necessarily has to be the way it is. It really just means that it has two or more paths through which charge can flow. If you look at this up here, this has its own path, right? Then this has its own path. And then the last one down here has its own path too. So it doesn't matter if this one went out, these two would stay lit. Inversely, if this one went out, these two would stay lit. They already have their own path. They don't need the other ones. They're independent circuits. Whereas the series circuit needs each other. This one doesn't need it. It's very nice to have this in your house, obviously, because if one light bulb goes out in your house, your whole power in your house isn't cut off. So anyway, hope you found the electric current and circuits review helpful, and I'll see you in class.